So far, we have learned two methods to convert the OH group of an alcohol to a better leaving group. Now, there is another leaving group that we can also use. And so alcohols can be converted into alkyl tosylates, which is a fantastic leaving group. An alkyl tosylate is composed of two parts. The alkyl group, which we call the R group here, derived from the alcohol, and the tosylate part, which is here, which is short for p-toluene sulfonyl, or the p-toluene sulfonyl group. Now, one of the reasons it's a really great leaving group is because when it leaves, it has resonance, and so it's resonance stabilized. So when we talk about this, right, a lot of times you'll see that tosyl group abbreviated as TS, and then you'll see when it's put onto an alcohol like this, you're going to see it as an R, and that's for the R group, or the carbons and hydrogens, the oxygen, and then there's the tosylate. So just to be aware of that when you look at it. Now, alcohols are converted to tosylates with treatment with p-toluene sulfonyl chloride, which is shown here, in the presence of pyridine. Now, this process converts that really poor leaving group of the OH into a really good one, which is that OTS minus. Now, tosylate's a good leaving group, as we mentioned. Sorry, if it broke up there, I was trying to move the slide and stopped it. All right, so tosylate's a good leaving group because its conjugate acid is a strong acid, as well as there's just a lot of resonance there. So let's look at the mechanism. When we come here to look at the mechanism, we are going to look at S-butane 2-ol. And so this is S-butane 2-ol. And what we see here, right, is that these groups are electron withdrawing, so that makes that sulfur partially positive. So what's going to happen is that these electrons are going to come in and they're going to attack that sulfur. And then chlorine is the most electronegative atom, so it's the one that's going to leave there. So chlorine leaves. Now, we follow our arrows and think about the things that do not change. And we see here the stereochemistry doesn't change. And now we have a protonated alcohol, right? And pyridine can come in. And it steals that proton in a proton transfer mechanism, and then those electrons go back on the oxygen. And now right, what we find is that the configuration is retained. So when we add that tosylate group, which is a good leaving group, we don't change from R to S. We keep our configuration the same. And the reason this happens is because the carbon-oxygen bond here isn't broken when that tosylate is formed. Now, because the tosylate is a really good leaving group, this molecule can now undergo both substitution and beta elimination, just like alkyl halides can. So when we come over here, and these are two other molecules that we're looking at. Generally, alkyl tosylates are treated with strong nucleophiles, right, to undergo the SN2 reaction, or strong non-nucleophilic bases to undergo the E2 elimination product. But by adding a tosyl group to the alcohol, now it can go through both the SN2 and the E2. Now, I want to talk a little bit about this SN2, right? So, because substitution occurs via this SN2 mechanism, the inversion of configuration results when the leaving group is bonded to a stereogenic center. What do I mean by that? Well, if we look here and say, all right, we have this alcohol, which is cis, okay? And we are going to form the tosylate version. So we're going to have the tosyl chloride and pyridine. And what we're going to find is that we are going to retain that configuration. All that means is the configuration isn't going to change. So it's still cis. But look, if we do an SN2 reaction, then we get an inversion of the configuration where this is now trans, right? Because we had a backside attack. Likewise, right, if we start with a molecule like this, where we have this chiral center, if we react that with a Cn minus in a substitution reaction, right, where these electrons are going to come in here and they're going to attack that chiral carbon, and then those electrons are going to go onto the oxygen there, what we would find is we would have an inversion of the configuration, right? So SN2 still will change that configuration, right? If we start with R, we'll end up with S. If we start with S, we'll end up with R. Now, I love summaries, and this is a really great summary slide. This is showing you, hey, look, we have an alcohol group here. We can add H2SO4, which is an acid, or we can add POCl3, and we can get a double bond here. We can add HX, or SOCl2, or PBr3, and get an alkyl halide. We can add the tosyl chloride and get a tosylate here. Then, at this stage, we can add a nucleophile and now go through either substitution or elimination reactions. So nucleophile or base. Nucleophile of substitution, base if elimination. So again, just a really great summary slide. This for us ends our adventure in this chapter into alcohols. In the next screencast, we are going to look at ethers.